We are now exploring Waterloo Maple software for analyzing the mathematical equations just now we have derived. Maple 2020 version is loaded and the active output screen is in front of you. That represents the graphical response of the program developed in Maple for quantum tunneling of alpha particles. We shall set the rectangular potential barrier in the region 2 with a width, say small a, and we can vary the size of the potential barrier width. So here the first variable that I have is this one. I can vary the width of the potential barrier. At the same time, I can vary the potential of region 1, but I am not interested in making it other than 0. Similar is the case for potential of region 3, say V3, that also I am setting to level 0. Now the potential barrier V2, that is for region 2, I can raise the height of this potential barrier as desired. The energy of alpha particle is less than V2 here. So we shall set it to some lower value than V2. Now I shall enable the real function psi, real part of the function psi. So here you can see that the wave is coming, getting incident at this point and then going further but with diminished value. Now I am reducing the width of the potential barrier. As the width of the potential barrier is sizably small, then you can see the transmitted wave going through the region 2, which is shrinked into the region number 3. As the size of the width of the potential barrier reduces, the amplitude of the real part of the wave reaching into region 3, we can call transmitted into region 3, is increasing. Now we can have a look at imaginary part of the wave. The wave function psi, imaginary part with green shade, you can see on your screen, and the complete wave function psi is appearing on your screen now. And if you like to see the probability density, it can also be seen. Now the whole story depends upon the width of the potential barrier. So as we go on changing that, we can see the effect. Here I am rolling the screen forward so that you can see the transmission coefficient T present in this case and the reflection coefficient. And if you like to see the animation rolling over time, you can have a look at this for a moment. So as the time rolls, the wave is advancing towards the barrier, crossing the barrier and penetrating through. So with increased transmission, with smaller size of the width of the potential barrier, you can have a look. Now if we reduce the barrier height, then the transmission probability increases and smaller energy alpha particles can transmit through the potential barrier when the barrier is much higher than the energy of the incident particle. Thank you very much.